Welcome back, everyone. I hope you had a good spring break. You had a chance to catch up on sleep and then have daylight savings mess up with that. And, but it will get better. I think I operate better with the daylight savings than the the non-daylight savings time. We're going to get back with regression. We still have, I hope we can finish this in 2 lectures, today and Thursday. Let me double check that I'm actually recording. Show recording monitor. Yes, I am recording. Okay. So last time we left off talking about general linear regression. I want to go over that again, but we're not going to do the exercises by hand because if you remember last time we left off, we were very angry with how annoying the equations have become when we're doing more advanced models for regression. And let me remind you that in this class, linear regression does not mean regression to a straight line. We strictly mean by linear regression that the system of equations that results from the regression model is itself linear. In that sense, polynomial regression that we covered also in the last lecture, although the polynomial itself is nonlinear, but the coefficients of the model show up linearly, so therefore it's a type of linear regression. There are also many other models that will show up where it's still linear regression because the parameters of the model show up linearly. To be more precise about our language and communication on regression, we're going to say things like regression to a straight line, regression to a polynomial, regression to an exponential or whatever, okay, so that we are more specific and unambiguous with how we talk about regression, okay? And last time we did this exercise, we said, okay, what if you have a non-conventional polynomial, a plus bx cubed? In other words, you don't have the x and the x squared terms, okay? Then you would have to go through the derivation, write in the sum of the squares, and then differentiate with respect to the parameters. And we did this together in class, and we derived the governing equations. Those are the normal equations, okay? And then we deduced the system of equations for the coefficients a and b. Then we also went ahead and said, okay, what if you want to regress data that is more like sinusoidal in nature? So in this case, this is a regression model, and it's a linear regression model because the coefficients, the parameters a and b, show up linearly. They're multiplying the sine and the cosine. You are given here data for time, and for t is your independent input variable, and y is your input data. So although there's sine and cosine involved, and those are highly nonlinear, it doesn't matter because we're not trying to fit sine and cosine. We're trying to fit the coefficients a and b, okay? And those show up linearly. Then we also did the same exercise. We wrote the sum of the squares. We differentiated with respect to the parameters. Notice my verbiage. We are trying to fit the parameters. We differentiate with respect to the parameters a and b. I'm showing them in red to emphasize that those are the unknowns, okay? And then we went through the tedious and annoying exercise. And I remember everyone was getting frustrated with this. I hope you still remember that. You might still have it on your notes. And then we deduced the system of the normal equations, the system of equations that governs the parameters a and b. And then we said, okay, let's say you have another model, a cosine t plus b sine t plus c e to the minus t squared. Then again, you go ahead and write the sum of the squares and differentiate, and it gets really tedious and annoying. And then I told you, okay, what if there is actually a better way to do it, at least in the case of linear regression models where the coefficients, the parameters show up linearly. And I had to introduce I had to remind you of the idea of basis functions because we want to do this generally for any linear regression model. And if you remember, we introduced these basis functions when we were doing interpolation, where interpolation didn't need to be interpolation to a polynomial or a straight line. We could interpolate any kind of model as long as the coefficients, the parameters show up linearly. Same thing here. The basis functions are elementary functions that you combine together linearly so that you can create more complicated functions. So in this case, cosine, sine, and x e to the minus t squared are all basis functions. The parameters are multiplying those functions, and they show up linearly. And if you remember also this slide from interpolation, where I list the basis functions for different models, a plus bx basis functions are 1 and x, a naught plus a1x plus a2x cubed basis functions are 1, x and x cubed. Same thing here for this one, a naught plus a1x and a2e minus x squared. The basis functions are 1x e to the minus x squared. So we know how to do this, okay? For this guy, log a x to the power b, if you split log a x to the power b, you get log a plus b log x, then you get a plus b log x, then your basis functions are 1 and log x. So you're allowed to do these sorts of manipulations. And over here, a cosine t plus b log t, you get cosine t and log t, okay? An infinite number of variations. Okay, to show you the method, and again, we covered this last Thursday, Thursday before spring break, but it's good to kind of try to refresh your memory again. I'll go a little faster though. To show the method, the methodology that is going to get you straight to the normal equations without having to do any annoying differentiation, any crazy summations, okay? I want to illustrate this concept just by an example with two basis functions, phi of x and psi of x. And those two basis functions, they're multiplied by two parameters a and b. That's our model. So you are given data x and y, okay? And we're trying to fit a phi x plus b psi x into that, to regress into those data. Okay. So if you go through the derivation of writing the summation, sum of the squares, and differentiating it with respect to a and b, this is the system of equations that you obtain. Okay, so we can show this. It's not a hard exercise to do. It's just a little tedious. Okay, but this is the system of equations that we obtain. And then I told you, okay, I want to rewrite this in an interesting way. On the right-hand side, you can split this 2 by 1 vector into the product of a matrix and a column vector. And turns out that this is what this is. This matrix is a 2 by n matrix, so it has 2 rows and n columns. And if you notice, on the first row, you have phi 1, phi 2, all the way to phi n. What do we mean by phi 1? It's phi at x1. Phi 2 is phi at x2. Phi 3 is phi at x3, and so on, like our notation that we adopted. Same thing for psi 1 to psi n. It's psi evaluated at x1, which is the first data point. Psi 2, psi at x2, and so on. So if you do the matrix vector product here, you get that exact thing over there. So you get phi 1 times y1 plus phi 2 times y2 plus dot, 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 plus phi n times yn. That gives you the first entry up there. And for the second entry, same thing, psi 1 times y1, psi 2 times y2, and so on. So we agreed that this product is equal to the true solution up there, or the true answer. Now, what's more important here is the left-hand side, or the coefficient matrix. And if you notice, that coefficient matrix, hold on, is composed of that same matrix over here and its transpose. Okay? Its transpose. Now, this matrix is very special. This matrix is very special. If you look at it, it consists of the two basis functions that we were dealing with. Okay, the first column contains the first basis function, phi, and the second column contains the second basis function, psi. But then the rows, they contain the observations. Phi evaluated at the first observation and psi evaluated at the first observation. And then same thing for the second row, second observation for phi and psi. Okay, so think of it this way. Columns contain the basis functions listed in the way they are listed in your model. So you write your model as, first basis function, second basis function. You stick to that, okay? And then the rows contain the observations. So these are actually values. These are numbers. You just take your basis function. It could be exponential, could be cosine. You evaluate it at x1, you evaluate it at x2, you evaluate it at x3, and you put it in this matrix, okay? So this is a n by 2 matrix, okay? This matrix is very special, right? We're going to call this matrix A for lack of imagination. We're going to call it the regression matrix. Again, I don't know what they call it. Different people call it differently. In this class, we're going to call this the regression matrix. When I ask you a question in the homework or the exam, I tell you derive the regression matrix A. Okay? So you should know that this is the regression matrix. Now, when you think about this, this is A. If you call this A, and you call that vector Y, okay, then the other two matrices are simply the transpose of A, right? So this is A, transpose of A is you just flip it around, okay? And then your vector of unknowns, call it alpha. Okay? Now what I'm claiming is to derive the normal equations for a linear regression model, you only need to know the matrix A. You don't need to write the sum of the squares. You do not need to differentiate that sum of the squares. All you need to know is that matrix A. And that matrix A is so easy to build because it's simply a replica of your model. Contains the first basis function, second basis function, evaluated at all the data points. It's like the simplest thing you could do to build the normal equations. You don't need any different, you don't need anything. All you need to know is your regression model and the input data. So you know A, then you can build the normal equations. At the end of the slides, with additional material, there's the full derivation of why this actually is the result of differentiation of the sum of the squares for an arbitrary situation. It's a very complicated proof. Okay, so you have to kind of trust me on this result. Okay, trust the mathematicians on this result. But this is it. All you need to know is A. This is a very, very powerful statement because we no longer need to do any summations, any complex differentiation to get to the normal equations. Okay, this is a very powerful statement. But it only applies to linear regression models. We're going to talk a little bit more later about nonlinear regression. Okay. So in general now, this methodology also applies to an arbitrary model, not just with two basis functions. You could have an infinite number of basis functions. You follow the same procedure, and here's how it looks like. If your model consists of m parameters, alpha 1, alpha 2, alpha 3, alpha 4, alpha m parameters, and m basis functions, okay? Number of parameters needs to be consistent with the number of basis functions. Those basis functions, I'm calling them phi1 of x, phi2 of x, phi m of x, and so on. Then your regression matrix looks like this. Again, the columns contain the basis functions the way they are listed in your model. So it couldn't be easier. You just take your model, you write it, and you put the matrix under it. In the first column, I'm going to have phi1, second column phi2, all the way to phi m, the mth basis function. And then the rows contain the value of that basis function at the corresponding observation. The first row is all the basis functions evaluated at the first observation x1. The second row are all the basis functions evaluated at x2, and so on, all the way to xn. Okay? This is not a square matrix. It is not a square matrix. You have m basis functions, so m columns, and n observations. Okay? So it's an n by m matrix. Okay? It is not a square matrix, and it shouldn't be. This is regression. In regression, we have more data points than we have parameters. Okay? Okay. So here's how we're going to use it. Given n data pairs in the form of x1, xy1, x2, y2, xn, yn, once we do some examples, the idea becomes very clear in your mind. You'll see. Okay? Then, in a linear regression model of this form, build the regression matrix A, and then build the y vector, which contains the value of the observed dependent variable, and then finally solve this system of equations, ATA alpha equal ATY. And we know how to do this, mp.linalgebra.solve. You give it This ATA is your coefficient matrix, and this right-hand side. And the solution vector contains the coefficients for the regression model. OK, let's do an example. If you remember, when we started with regression to a straight line, our model was a plus bx. And the normal equations were written in matrix form like this, right? If you don't remember, go back to the first lecture. That was the system of equations, n, some xi, some xi, some xi squared. So if we use this methodology of using the regression matrix A, we should obtain that same answer, right? OK, let's do it. I'm going to do it with you now, OK? So first, you write your model, a plus bx. Next, you list your basis functions. Basis functions are 1 and x, OK? Your regression matrix A looks like this. In the first column, it contains the first basis function, 1. And in the second column, it contains the second basis function, which is x. Now, the rows go from the first observation to the second observation to the nth observation, however many observations you have. When you're deriving this system of equations for a generic case, you just assume you have n data points, OK? That's it. That's all you need to build, to recover that system of equations, that answer that we obtained by doing so much work early on. OK, alpha is your solution vector, contains a and b. And your right-hand side, your y, contains your y data points that are given to you, y1, y2, all the way to yn. Remember, x and y data are given to you, x1, y1, x2, y2, and so on. Now you build the left-hand side, which is A transpose times A. This is A transpose. Now, when you multiply this, this is 2 by n times n by 2. So it's going to give you a 2 by 2 matrix. So we're on the right track. OK? Now, when you do this, this is exactly what you get, right? Because this is 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1, n times, that's n. OK, this guy is 1 times x1 plus 1 times x2 plus dot, 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 1 times xn. That's sum of xi. Same thing over here, x1 times 1 plus x2 times 1 plus xn times n, sum of xi. And the last one here is x1 times x1 plus x2 times x2 plus dot, 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 xn times xn. It's sum xi squared. And that's the coefficient matrix we obtained when we did that full derivation with the least squares, OK, with the differentiation, et cetera. And on your right-hand side, you simply multiply the transpose of A by your column vector. So this is a 2 by n matrix times a n by 1. So you should get 2 by 1, vector. And that's what you get. 1 times y1 plus 1 times y2, et cetera. So you get sum of yi. And for this one, you get x1 times y1 plus x2 times y2, et cetera. So that's sum of xi, yi. And that's exactly the answer that we obtained when we did the full derivation. Connor.
Why can't we take A transpose out of both sides of the equation, just that A times alpha is equal to y?
Because that becomes an overdetermined system, okay, right? So you have to have, the coefficient matrix needs to be squared for the system to be invertible, right? If you didn't have, if you only had A alpha equal y, you can't, it's like you're trying to do interpolation on more data points than you can afford, okay? So that's kind of how it works, luckily. All right. So procedure is simple. Write your model first. Identify what your parameters are. Get your basis functions. All you need is to get the matrix A. You assume you have x1 all the way to xn and y1 all the way to yn. And that's it. That's all you need to derive these normal equations. These are the normal equations, all right? So now, go and do it for a quadratic. Remember, for a quadratic, when we did the full derivation by hand, with the differentiation of the sum of the squares, etc., this is what we obtained. Now, I want you to use the normal equations, the regression matrix A, sorry, to obtain this same system of equations. Okay? So first, write your basis functions, and then build that matrix A. Okay? Assume you have n data points, x1 to xn, okay? And y1 to yn. We're trying to derive the equations, the normal equations for a quadratic fit using the regression matrix A. Okay? This is the regression matrix A. Just once you get to that one, then you can build ATA equal ATY. But just get to this point, get to build that matrix A, and you're halfway through. If you want, I can go back to show you what we did with the regression to a straight line, except now you're going to do it for a quadratic. So you have cx squared. Okay? So you have plus cx squared. Go ahead, try to do it by hand. Assume you have n data points. If you don't know where to start, start with that regression matrix A. First column is the first basis function. Second column is the second basis function, which is x. Your third basis function is going to be x squared, right? So your third column is going to contain x squared. And do it all the way to n data points. So remember, we're doing, this is for the straight line. We're going to repeat the same thing, but for a quadratic. So you have plus cx squared up there. And you're trying to find A, B, and C. Perfect. Wow. Good job. Perfect. Perfect. All right, so now, yep, you got it. So now continue and build ATA equal ATA times alpha equal ATY. So build this now and show that it's going to be equal to that answer that I showed, okay? Good work. Good work. Yeah. But no, yep, perfect. Perfect. Yep. Yep, perfect. Yep. Try to do it. Yep. Most of you got the regression matrix A. So now go ahead and do the ATA and the ATY. Yep. Yeah, so now you got, now this one is going to be, whoops, did I touch anything? Yeah, so you got this one, this one, this one, this one, and this one with this one, and then this one, this, and then you're going to have x cubed, right? So you're going to have x1 times x1 squared plus x2 times, so you have sum of xi cubed, right? Yeah. Yep, you got it. Yep. So now transpose it, multiply by the transpose.
How do you guys write x squared, x1 squared, x2 squared, xn squared?
Yeah, so put 3 dots though, so that you know that there's more. Yeah. So that you know it's in an arbitrary number of points. Yeah. Not just 3 exactly. Yeah. Well, put them vertically, so that because you're going. You're going x1, x2 right through xn. Okay. Who got the regression matrix A? I see many hands. Okay, good. Yep. So remember now, once you get that, do the multiplication A transpose times A to get this coefficient matrix, and A transpose times Y, you're going to get this vector for the right-hand side. Okay? Want me to go back to the previous slide? This is with the straight line. Okay. Give you another minute. Do you think this is easier than having to do all the differentiations with the S, right? It's just a matter of plugging in some values. And once we hit Python, you can do this whole thing in like one line of code. Okay? It's pretty powerful.
One line?
Mm-hmm.
Actually, one?
Actually, one line to build that matrix. To build, well, one line. Importing things doesn't count, right? Because you have to import, like, you might as well have Python auto import for you. Come on, Miles, let me make the point. Always have to bicker. But yeah, one line to build the matrix A. And I'll show you in a minute. Okay. So this is my answer. Basis functions are 1, x, and x squared. My coefficient matrix, the columns contain the basis functions. First basis function is 1, second basis function is x, and third basis function is x squared. Now I build the rows. I go x1, at x1, at x2, at x3, all the way to xn. My solution vector is ABC, that's alpha, and my right-hand side is y1 through yn. Now I simply take A transpose times A over here, and A transpose times y on the right-hand side. So transpose, you take this matrix, okay, and flip it. So this is what we get. So if you're confused about the transpose, you take the first column, it becomes the first row, the second column becomes the second row, and the third column becomes the third row. Then when you do the multiplication, you get exactly the answer that we had so hardly derived with a complicated way of doing it. Okay, so now let's make it a little harder. Let's go ahead and derive. We also derived this, if you remember, by hand the Thursday before we left for spring break. It was annoying. Now try to derive this again, this model, a log x plus b cosine x, using this regression matrix A. Okay, so write down your basis functions, build the matrix A, multiply by the transpose, and you're done. You got the normal equations. Probably should put a copy of that regression matrix for you. Let me do that. Give me a second. Just get that coefficient matrix. Assume you have n data points. First column is first basis function. Second column is second basis function. The best part, doesn't matter how you list your basis functions. You could put b cosine x plus a log x. It doesn't matter. Okay? But as long as everything is consistent. Your solution vector for the parameters needs to be also listed in the order that the model is listed. So A, B, if you put them BA, it needs to be BA. Okay, so if you swap those basis functions and the parameters, you need to list things in the right order. Okay, I will give you the same answer. Yep. This is a classic exam problem. Okay? Yeah, so I think you have them the other way around. Right, yeah. Yeah. Yeah, so your A matrix, yep, you got the log and the, well, no.
Oh,
You got it messed up, yep. This is your A matrix, ATA should be, right?
Okay.
So this should be on the left. Otherwise, you can't do the multiplication. Yeah, the inside number of the matrix size needs to be consistent with the outside number of the next matrix. So n by 2 times 2 by n, for example, or 2 by n times n by 2, right? Yep. Nope, you got it. Well, there's no 1 here, right? The basis functions are log and cosine. Right? So there's no 1. In the other case where we had a polynomial, we had a times 1 plus b times x, right? Plus c times x squared. And then, therefore, the first basis function was 1. But here you don't have 1 as a basis function, right? So, yep. Okay. Yeah?
You scared me when you walked by. That's all.
You don't have a question?
No.
No? Okay, perfect. I didn't mean to scare you.
Oh, and also good news. I have docs on my phone, so I was able to write down the life hacks.
Well, thank you, Miles. All right. Yeah, so the A transpose needs to be on the left-hand side of A. I didn't even look. I was like just kind of, I was looking for a paper but I didn't see anything. Yeah, so A transpose times A, right? Yeah, A transpose times A. Okay, guys, the transpose multiplies everything from the left-hand side. Otherwise, you cannot do the multiplication, okay? The transpose multiplies the A matrix from the left-hand side. Always remember ATA, okay? ATA. So this is, my basis functions are log x and cosine x. There's no 1 in the basis functions, okay? When we had the polynomial of the straight line, one of the parameters was just a free parameter, was multiplying 1. So 1 was the basis function. But here, there's no 1 as a basis function. Your basis functions are log x and cosine x. Your regression matrix, first column contains the first basis function, log x, and the second column contains the second basis function, which is cosine x. Then the rows, you start building the rows, log x1, cosine x1, log x2, cosine x2, etc. Once you have A, you're done. Then you multiply transpose by A, okay? Those matrices need to be in this order, otherwise your multiplication is not, you can't do the multiplication, okay? To do the matrix multiplication, this is 2 by n matrix times n by 2. And the inside two numbers of a matrix multiplication need to be equal. And they disappear, so you get a 2 by 2 matrix. Okay? So you all were able to show this, so that's it. You get the normal equations without having to do any tedious or annoying differentiations. Okay? It's pretty powerful. All right. So now, how do we do this with a single line of code in Python? Again, the single line of code is for the coefficient matrix for A only. Now, you still need to take the transpose and multiply it, etc. But that single line of code, there's a really cool function in Python called column stack. So it's numpy.column stack. The column stack, what it does, it takes an array and puts it in a column. So when you think about this matrix, this is all phi1. So if you have a basis function, let's say cosine x, and you apply it to an array of x values, x1, x2, and xn, you're going to get an array of y values with the basis function. So cosine x1, cosine x2, and so on. NumPy.columnStack You give it that array, phi1 at xi, at all the xi, it puts the entire array as a column in a big matrix. Okay? And then this is exactly replicating what the A matrix looks like. Then the second column contains phi2, also evaluated at all the x values. Okay? Remember, in Python, when you're dealing with NumPy arrays, if you give numpy.cosine in NumPy array, it's going to produce a NumPy array with cosine applied to each entry. Okay? So phi2 at xi is a NumPy array, and under column stack, it puts it in a column here as the second column, and all the way to the last basis function. More specifically, this is how I would do it. Import NumPy as NP. And suppose you're given xi and yi data. So those could be parsed from a text file, or you've entered them by hand. Then you build your matrix A as numpy.columnStack. Phi1, whatever your basis function is, could be cosine, exponential, np.log, could be xi squared. Okay? And you just build A. Then you build the left-hand side of that, of the normal equations, which is A transpose times A. Remember, early in the semester when we talked about matrix multiplication, you use the symbol at to do matrix multiplication. Okay? So that gives you the left-hand side. Okay, that's the final coefficient matrix of the normal equations. And this needs to be a square matrix. Now the right-hand side is A transpose, so that's A transpose, also multiplied at yi, which is also an input data. Okay? And then solve ATA and right-hand side. You're not solving A and right-hand side. A is not a square matrix. You're solving A transpose A equal the right-hand side. Okay? Give a couple of examples, and then we'll do something together in Python. So for example, to do this regression model, A plus bx, you have the basis functions 1 and x. This is all I have to do. numpy.columnStack np.ones of size n and xi, right? Same thing for the quadratic. My basis functions are 1, x, and x squared. So I'm going to stack 1s, I'm going to stack x, I'm going to stack x squared. Okay? And that's all you need to do to build this matrix A. Okay. Get your Jupyter notebooks up and running. We're going to build this from the ground up. This is a problem from one of the textbooks I use for this class, from Chopra and Canali. And the problem is given by the following statement. 3 disease-carrying organisms decay exponentially in lake water. So this could be like algae or some bacteria in a lake. Okay, this is an important problem when you're trying to measure bacterial growth in like lakes, and then for public health they need to know these data so that they tell people, oh, don't go to Bear Lake this weekend. There's a huge growth of some bacteria, and then they decay naturally, something as they consume resources, etc. So apparently there's 3 disease-carrying organisms in a lake, and they decay exponentially according to the following model: A e to the minus 1.5t plus B e to the minus 0.3t and plus C e to the minus 0.05t. Now t in this case is time. P is the population, the bacterial population, could be in millions or thousands, okay? Now they're asking to estimate the initial population of each organism. What is the initial population? It's at t equals 0. And at t equals 0, the initial population for organism A is A. For the second organism, it's B. And for the third organism, it's C. Okay? And you have only the following measurements taken at 0.5 hours, 1 hour, 2, 3, 4, 5, 6, 7, 9 hours into the growth of these organisms. And the population size is decaying. You know, it starts with a total population of 6, okay? But we don't know the individual populations, okay? Well, it starts at 0.5 hours with 6, okay? And then 4.4, 3.2, this could be in millions. Okay? So we're going to do this in Python together. Let's grab a fresh notebook, Or you could copy an existing notebook because I need matplotlib and NumPy and all of those imports, good imports that we use. Okay? We're going to do this together. Just get a Jupyter notebook up and running. Import the boilerplate from a previous Jupyter notebook. That's always what I do. We're going to need NumPy and we're going to need matplotlib. Okay? Now I'm going to put in the arrays for this problem. The data, the input data. Let me see. Okay, so the input data. Move to pressed on. Whoops. Overwrite. Okay, where is Keynote never likes to show up exactly where it's supposed to. Okay. All right, let's see. Okay, I'll just read it from here. I cannot move it to the other. All right, so it is really confused. Okay, so this is the data. Our xi data, or let's call it ti if you want, or xi, whatever is comfortable for you. Let's call it ti to confuse things a little bit. So ti is equal to numpy.array. So I'm going to enter this by hand because it's a small array. But in practice, you'll probably have to get this through a text file or a CSV file or some data collected from experiments and so on. Okay. Let's see. So we got, for time, we have 0.5, 1, 2, 3, 4, 5, 6, 7, and 9. Okay. Oops. 9.0. Okay. Okay. And for the yi data, which is the population size, so pi, I'm going to also declare an array, numpy.array. And we're going to do 6.0, 4.4, 3.2, 2.7, 2.2, 1.9, 1.7, 1.4, 1.1. Okay. All right. First thing I want to do when presented with data is I'm going to plot it. And always plot a scatter. Don't plot it connected with lines, because if the data is all over the place, it's just not right. Okay? Let's do plt.plot, and we're going to plot ti on the x-axis and pi on the y-axis, and I'm going to give it the symbol disk. Okay, so this is our data. Well, as expected, it kind of decays exponentially. It's not an exact exponential because you see it kind of bulge up a little bit here and then flatten out. Okay. So now our objective is to fit this model, a, e to the minus 1.5, etc. And the parameters are a, b, and c. Okay? And in our regression, we are going to solve for a, b, and c. And that turns out to be what the problem is asking for, because a, b, and c are the initial populations of these organisms. Because at t equals 0, you're going to get a and b and c, right? Okay, for each population. So the way they built this model is that they probably knew that the first organism decays at a rate of e to the minus 1.5 t, and the second organism is at a rate e to the minus 0.3 t, etc., by studying populations of organisms, right? So that's how they built up this model. Okay, I don't think we need the slide anymore. Okay, so first thing I want to do first is kind of build up that matrix A. A is mp.column stack. If I press tab, it automatically completes. Okay. Now, with the column stack, I want to put my basis functions. So our basis functions are, in this order, e to the minus 1.5t. The second basis function is e to the minus 0.3t. And the third one, e to the minus 0.05t. You all with me? Okay. For column stack, we're going to put those exactly as they show up. So you open parentheses, but then I'm going to put them in brackets. And the first one is going to be np.exp minus 1.5 times what? Not t, ti, right? Because this is going to be the first basis function evaluated at t1, evaluated at t2, evaluated at t3, right? So if you look at, okay, so let's see what this does actually. If you look at this, what is this? This is a column vector of numpy.exponential e to the minus 1.5 applied at first observation, second observation, third observation, fourth observation, and so on. Okay? That's the first basis function, observation 1, 2, 3, 4, etc. So we follow the same way. Then I'm going to put a comma for the second basis function, and that is np.exponential, what was it, minus 0.3t. Okay, so minus 0.3 multiplied again by ti, because I need that basis function to be evaluated at all the input data points, t1, t2, t3, t4, etc. Okay? And then finally, np.exponential minus 0.0, what is it, 5 times ti. Now, if you look at this matrix A, first base, it has 3 columns, exactly as we expect, because we have 3 basis functions. First basis function, second basis function, third basis function, evaluated at t1, t2, t3, t4, etc., all the way to the last t. This is not a square matrix and should not be a square matrix. It's the number of, it's n, number of data points, times 3. Now we're going to multiply this one from the left by A transpose to build the actual coefficient matrix of the normal equations. The equation, again, the normal equations, they govern the regression system. They govern the coefficient, the parameters A, B, and C. Okay? When we solve the normal equations, the answer is A, B, and C, the parameters. Okay? So now, ATA, that's what I usually use, is A dot T, which is the transpose of T. So NumPy arrays or NumPy matrices, you do A dot T, it takes the transpose of A. Okay? And then I'm going to multiply it by A. So that gives me ATA. And if I print ATA, what is the size of ATA? 3 by 3, right? So if you're kind of confused about it, just ask yourself, how many unknowns do I have? We have 3, A, B, and C. So our system of equations needs to be 3 by 3. Okay? So if I print ATA, indeed it is 3 by 3. Okay? 3 by 3. Correct. Good sanity checks, okay? Now the right-hand side is A transpose times the input y data, which is pi. Agreed? So those were our y data points. Call them pi. Okay? Finally, to get the solution, mp.linalgebra.solve. What is the coefficient matrix of the system? It's ATA, not A transpose. What is the right-hand side? It's right-hand side, RHS. Now, solution, if I print it, solution contains what? A, B, and C in that order. That's the initial population for the first organism, initial population of the second organism, initial population of the third organism. Okay. This is still at ASCII level, so we ASCII, okay? We need to visualize this. So let's now plot our model All right, so we're back in action. Okay, now I'm trying to create this model in Python so I can plot it. I'm defining a routine that implements this model so I can plot it with the A, B, and C that we just obtained. Okay? So let's do it. This is going to be A times mp dot exponential minus 1.5 times t. I'm not putting ti here because this is a routine. It's going to take values of t. I'm defining t over here. Okay? Plus b times mp dot exponential minus 0.3 times t, correct? Plus c times mp dot exponential minus 0.05 times t, right? Minus 0.0. Okay. All right. Perfect. So now to plot this model on top of the original data, I'm going to copy this guy here. Okay. And then I'm going to create a lint space of a lot of data points so that I have a nice smooth plot for my model. Okay. So I'm going to declare a new variable, mp.lintspace, that goes from the minimum value of ti to the maximum value of ti. Okay, it defaults to 50 points. And then I'm going to plot it. So plt.plot the new t values. And I'm going to plot the model now, okay, on those t values. Now this model, the way I designed it, it takes three parameters, a, b, and c. So you could put sol 0, right, that's a, sol 1, that's b, and sol 2, that's c, right? Because solution, sol, contains a, b, and c. Are you with me? So if I do that, look at that. That's our regression model. It's almost perfect visually. Okay? Okay, are you ready for a little trick? Yes, no? Okay, get it to plot. Okay, you ready for a little trick? You saw how annoying it was? We have to deal with annoying things all the time, but Python always to the rescue. We had to put in sol 0, sol 1, sol 2. What if you had a model with 16 parameters or 168 parameters? Do you put them all like this, sol 0, sol 1, etc.? There's a little trick in Python that allows us to pass an array of arguments over here. So we agree that sol contains those coefficients, a, b, and c, right? If I pass star sol over here, star sol, this is called a dereferencing procedure, but just don't worry about that. If I pass just star sol, it has the equivalent effect of passing a, b, and c, sol 0, sol 1, sol 2, or however many parameters you have. So from, yes?
That still doesn't solve the fact that, like, the model equation, we had that many solved things when our model equation also have equally as many.
That's fine, but passing the arguments, you don't have to type in every parameter, right?
Yes. There's
Yeah.
a lot of times, but
Yeah, I mean, in the end, you have to kind of, at some point, you have to write in a times basis function 1 plus b times basis function 2, right? So there's no way around that. But at least you don't have to pass. Now for this model, when we calculate the r squared value, okay, imagine you're dealing with different models that have different parameters. Do you create an r squared function for each of those models? Because they have different parameters. You don't want to do that. So this procedure allows you to bypass that. Okay? Yes?
Does like the solution matrix have to be the same length as the number of variables you define in your model?
It is by definition that, right? Yeah. Now, you could declare A, B, and C globally, and then you don't have to deal with this issue. But if you're doing it this way, that's a more efficient way to do it. Okay? Okay. So we can also compute the R² value. And if you remember, well, probably don't remember. Let's go ahead and create an R² function. I'm not going to go through the details of, we did the R². We spent the entire lecture that last Thursday. So I'm just going to define the R² value over here, the R² function. Unfortunately, there's nothing straightforward in Python that gets you to get R² values, which is so weird. Not polyfit, not whatever functions we're going to learn to use later. So you have to always kind of hard code your R², okay? Pardon me? Okay, so I'm going to define my R², and my R² needs xi data and yi data, a model, and a bunch of parameters, or let's call them params, okay? So those are the parameters of the model. Notice I'm assuming that params is going to be an array of parameters because I want to be able to reuse this function for any regression model that we're going to be dealing with for the rest of the semester. Okay? So I'm going to use that feature of dereferencing *sol to pass those parameters around. Okay? So we don't have to put A, B, and C, or A, B, C, D, E, F, G, etc. Okay? Now, for the R² value, we had to calculate y bar was the MP dot average of yi, and then the fi values, they were the model evaluated at xi and star params. Okay, and then result was, just write this as is. The formulas are in the slides, so you can connect the dots over here. If you remember, this was 1 minus numpy dot sum of yi minus fi squared, okay, over numpy dot sum of yi minus y bar squared. Remember, we're trying to assess if the regression is better than using the mean to describe the data. That's what the R² value does for you. Okay, and then return results. Okay, now this, guys, is a generic R² function. You feel free to use it in your other classes. Okay, take xi data, yi data, a model, and a bunch of parameters for that model. And it doesn't matter how many parameters the model has. It doesn't matter. Okay? Now, the way you call this is R². In my case, I have ti as the input xi data and pi as the input yi data. My model is called model. Okay? And params is simply the solution. Okay? Now, when I run it, it gives me a 99.7% R² value, which is an almost perfect fit. Okay? Which tells me that the data has been doctored, most likely. But still, this illustrates the process. Okay? There's this level of R² so close to 1 is quite unrealistic. Yeah. And in a way, this is understandable because we're illustrating here to you the idea of regression, right? If you go back to the femur and height problem, we had a more realistic R². I think we were at like 92% or 90%. And those are very realistic R² values. Okay? I mean, by saying the data doctored, I think the authors of this problem, they created those data using the model and they perturbed it a little bit, right, to create some error in it, okay? But you almost never get this level of confidence, this level of R² in observations. Experimental error alone is going to mess up with the data so much, okay? All right. Let's do another problem. This one is a little more interesting. Environmental engineers dealing with the impacts of acid rain must determine the value of the ionic product of water, Kw, as a function of temperature, water temperature. Scientists have suggested the following equation to model this relationship. Minus log 10 of Kw equal A over Ta plus B log 10 Ta plus CTA plus D. Okay? Ta is the absolute temperature. A, B, C, and D are the parameters. Okay? Now employ the following data and regression to estimate the parameters. Okay? So the first question to ask is this a linear regression problem? Well, you have Kw, yeah, you're solving for log Kw, right? The parameter, someone else said yes, over there, yeah. It is, because the coefficients, all I care about are the coefficients. How do they show up? They show up linearly. A, B, C, and D, they're not under the action of sine or cosine, or they're not kind of under weird functions combined with the independent variable. Although you have 1 over Ta and log 10 Ta, that doesn't matter because Ta is a given value to you. Okay? As far as we care, the coefficients show up linearly. And you're given these data, temperature in Kelvin, absolute temperature, and the ionic product, Kw. Okay? So we're going to build this using the regression matrix A. Okay. So I'm going to go ahead and copy this notebook. So keep these notebooks with you. We're going to come back to them. We're going to solve them with in another way. Okay? So I would just make a copy of this notebook. We only need to change these data here. This is my keynote. Okay. Okay. So now my data, I'm going to change the naming to TA, T, and KW. Okay. So I guess it stays as TI. We're going to call it capital TI and KWI. Okay, those are my inputs, right? So we have 273.15. Let me see. 273.15, 283.15. Let's see. Okay. 273.15, 283.15, 293.15. I just noticed that they have the 0.15 in all of the data points. 303.15 and 313.15. Okay? And the KW values 1.164. So 1.164 e to the minus 15. It's a very small number. And 2.950 e to the minus 15. I mean, I could multiply the whole thing by e to the minus 15, but it's okay. 6.846, 846 e to the minus 15, and then 1.467 e to the minus 14, and then 2.929 e to the minus 14. Okay? Again, I expand this so you guys can see it. Yes, overwrite. Stop asking me. Okay. So first thing I'm going to do is plot the data. On the x-axis, I'm going to plot the temperature. On the y-axis, I'm going to plot the ionic product. And it looks like this. Like some exponential. But look at how small the y-axis is. Talking very, very small numbers. 10 to the minus 14. Okay? But that's Kw. All right? That's Kw. However, our model is minus log Kw. So we really need to plot, on the y-axis, we really need to plot minus log of Kwi. Agreed? So if I do it over here, minus mp.log 10 of Kwi then that becomes, swaps it. It's almost linear, right? It's almost linear, but it's not. But however, now the y-axis is kind of order 10. So we have some reasonable values. We don't have to worry much about round off. All right. So okay. All right. So let's see now. For this one, my y data needs to be minus log 10 kW. So I need to process this a little bit, and I'm going to call this kwi underscore. And I'm going to say this is minus mp.log 10 of kwi. Okay? So then here I can plot kwi underscore. Tick, tick. Okay? Makes sense? Because that's going to be my right-hand side for my regression model. Minus log 10 kwi is going to be the right-hand side, part of the right-hand side. The rest is almost identical, okay? So now, what are our basis functions? We have 1 over t, log 10 t, t, and 1 in that order. So here's what I'm going to do. I'm going to put 1 over ti. The second basis function is mp.log 10 of ti. And then the third basis function is ti, and the fourth one is 1. Now, I can't just put 1 because this is, if you do this, it's gonna crash through an error. Why? Because 1 is not an array, it's a single value. So really here we need a NumPy array of 1s. How many? However many data points you have. All right, so we add this. So now it's 2 lines of code, Miles. N is len of ti, okay? And then here I have np.1s. I mean, you could put it into one line over here. np.1s of size n. And now it works. Okay? We have 4 basis functions. First basis, second basis, third, and look at the ones over here. Fourth basis function. Okay? And then you don't change a thing over here. ATA, and right-hand side is AT times KWI, but the minus log 10, so the underscore. Okay? And then if I solve it, these are my coefficients now. A, B, C, D. Are we in sync? Yeah? We have 5 minutes, so we should be okay to finish this today. Any errors? Concerns? No errors there. Okay.
Did you run your line 10 yet?
Pardon me? I did, yeah.
You did?
Yeah. Yep. So maybe, did you get a different answer?
Yeah.
Maybe in the data?
No, because the plot's right.
Okay. So maybe here?
Yeah.
Next, I'm going to define the model. Now, this model has 4 parameters, A, B, C, and D. Okay? So I'm going to define the model. That model is going to take a temperature. I'm going to call it TA. And then A, B, C, and D. Now, we know how to pass those parameters with the dereferencing operator, which is great. So all we have to worry about is defining the model over here, which is A over TA. So A over TA plus B log 10 TA plus B times np.log 10 of TA plus C times TA plus D. right? Now we're going to plot again our data, plt.plot ti and kwi underscore. That's the original data. The new temperature data, so that I plot the model. I create a lin space from the minimum input temperature to the maximum input temperature. Create 50 points in between, so I have a nice smooth curve. All right, and then we plot the model versus t. Now the model, again, is going to take t as the independent variable as simply star sol. And look at that. Perfect fit. Okay? Yep, so regression, the r squared. What do you think the r squared is going to be? Almost 1, yep. So someone already calculated the r squared. Okay, now the best part, we can reuse this r squared, and we just give it ti and kwi, and look at that, 100%. So this tells me that this data was actually created from the model and then given to us so that we try to regress it again. Yeah.
What's the data supposed to represent again?
The ionic product of water. So, yep. So I think what they did here, they created this model first, and then they deduced the kW, and they, gave it to us. So, all right. On Thursday, I want to finish with regression. We're going to learn about, so far, we don't know of any other function in Python that could do linear regression with arbitrary basis functions, right? Because polyfit could only do polynomials. You cannot even mess with that polynomial. It needs to be a0 plus a1x plus a2x squared. You can only set the degree. You cannot take out any of the coefficients or any of the terms. So we had to learn about this regression matrix to do arbitrary basis functions. Now the question is there a Python function that could do arbitrary basis functions? Yes. We're going to learn about it on Thursday, but it comes with a big responsibility. Okay? And it's actually going to be using nonlinear regression to fit a linear model, which is a degenerate case. We'll talk about that on Thursday. But then you'll have another way to do this, what we've done here, ATA, etc. However, I hope that I've convinced you that this regression matrix A circumvents all the trouble you have to go through to differentiate the sum of the squares. All right? I'll see you on Thursday. Thank you.